Alrighty, I guess we're ready to get started. That's even on. Okay, good. So we have a quiz tomorrow in section as usual. Same drill as the last two quizzes. We will include some reference material, and you can find either in Piazza or the course website a pointer to the PDF of the material we'll be including, just in case you need to know. But it will be everything you need. So in order to talk about beta instructions in terms of the binary encodings and things like that. So hopefully that'll prepare you. We also have the Lab 5 checkoff due tonight. And then just as a reminder, Lab 6 was going to be due next Thursday. The Lab 6 will take you longer than most of the other labs do. It's also worth a lot more points. So that's a good lab to get a head start on if you haven't already. So today's lecture is going to be full of the word virtual for a while. It's sort of our theme of this week. The idea is that what we're going to do is start down the path of creating a virtual machine, which is just a fancy way of saying what we want to do is to make sure that we can take the hardware that we have, you know, the disk and the network interface and the video monitor and the CPU, of course, and share it amongst a bunch of different running programs, hopefully with a fairly low overhead. So we're able to switch from program to program to program. We'll be able to time share the machine amongst a lot of different programs that are all running simultaneously. And each of the programs will have the illusion of having a complete machine to itself, and that's the virtual machine. So what we're working on today is technology to sort of timeshare one physical piece of hardware and create the illusion of many virtual pieces of hardware, many virtual machines. And our first step in that direction, which we got started on last time, was virtual memories. So what we have is we have the CPU that's producing a virtual address, and we treat that virtual address. So here's the 32-bit address coming out of the CPU. So we have the virtual address. So that's the address that's produced by, that you think of when your program is running and producing addresses. That's the address that we're talking about. And what we want to do is we're going to treat this as sort of a two-component address. There'll be a page offset, which is some number of low-order bits, and then a higher number, so we have and then a virtual page number. So we're sort of splitting the address space into a bunch of pages. You can think of those as contiguous little sections of the address space. Typically, they're maybe 2 to the 12th bytes, 2 to the 16th byte, something like that. So some 12 or 16 of the bottom address bits are used to indicate where we are on a particular page, and the rest of the 32. So altogether we have 32 address bits on the beta, and the rest of the address bits we treat as the page number. And what the MMU does is that it translates a virtual page number into a physical page number. It's just a very simple table lookup that allows us to take a particular range of virtual addresses and turn them into the same size range of physical addresses, but not necessarily located. So here we have virtual page 0 sort of looking like it's mapping to physical page 0, but there's really no reason why the physical page has to have the same number as the virtual page. So the idea is that the MMU, its job is to come up with a physical address which has the same page offset, but in its high order bits has the physical page number. So the MMU does that mapping. Yes?
A page is just a group of consecutive memories.
Right. So it's in some ways you can imagine we could map each physical address to each virtual address to a physical address, but we'd have to have 2 to the 32 separate translations, 4 billion separate translations, which is far too many really to implement. So what we choose to do is instead do the translations page by page. So a page is really just a collection, as I say, of 4096 or 8192 or some power of 2 number of bytes that we're going to treat sort of as a chunk. And we'll move that chunk from disk into main memory, and then back and forth that way. So all of our memory management is going to be at the page level for this sort of discussion. And we have these two extra control bits in the table. One is resident, that tells us whether or not that virtual page is actually present in the physical memory. And the other is the dirty bit that keeps track of whether, when it comes time to throw that physical page out of memory, if we want to throw that virtual page out of memory, whether or not it's been changed, it has to be written back onto disk, changed by a store instruction. So our translation mechanism really is a three-step process. The first stage, what we're going to do in order to get reasonably high speed, is to take the virtual page number and look it up in a small cache, a so-called translation look-aside buffer, and to see if we have the VPN to PPN translation cached. Because the tables that we're talking about get pretty large, and we don't want to put them all in fast RAM. So instead we use a very fast little memory. So this typically happens quite quickly, and it's like a fully associative cache. It can be, a 16 entry or 64 entry fully associative cache, and it will have very, very high hit rates, because once we start dealing with a particular set of virtual pages, we're likely, for many, many accesses in a row, to access the same virtual page. And if we have the physical page number, then we can quickly come up with the information we need to complete the address. So we combine the physical page number with a page offset. We know exactly where to look in main memory, or in fact, typically in the cache first, the actual memory cache first. And then if we miss in that, we go off to main memory. If we don't have the information we need in the translation look-aside buffer, we have the slightly more time-consuming process of using the virtual page number as an offset into a table that's typically stored in actual main memory. And we can fetch the information from there, but that would be an actual memory access that we have to make. That information can be used to complete the translation process to come up with the actual address. And at that point, we often cache the physical page number information back in the TOB, so that once you've accessed a virtual page, and have to go through the translation through the page table, once that translation is complete, we'll put it in the TOB so that subsequent accesses to that virtual page go much more quickly. Okay, and then finally, if the page is not resident, if the R bit is off, then what we need to do is to go off and as we described last time, deal with this problem of not having the page physically resident in memory. So now we'll read it in from disk. So let's go through some quick examples. So we've arranged a very, very small memory system here. We have pages that have 8 bits of the address are being used as the page offset. So how big is our page? 2 to the 8th bytes, right? 256 bytes. And then we have a 12-bit virtual address and an 11-bit physical address. So we have 4 bits of virtual page number, so 2 to the 16th virtual pages, and 3 bits of physical page number, so we only have 2 to the 3rd, or 8 physical pages. So here's the entire page map. And how many entries are there in the page map? We need 1 for each virtual page. So there's 2 to the 4th virtual pages. So we have 16 entries here. And you can see that some of the pages are present in our 8-page physical memory, and some of them aren't. And in fact, at most we can only have half of the virtual pages in our physical memory at any given time, because we only have half as many physical pages. So if we go off and say, okay, I want to do a load from address 2C8, our first job is to divide that address, the hex 2C8, into a virtual page number and a page offset. Well, handily, our example has made it pretty simple for us to do that, because the bottom 2 hex digits, the bottom 8 bits are 2 hex digits of the address or the page offset. So in this case, the page offset is C8, and the virtual page number is 2. Everybody happy with that? What I've done is I have to go look carefully about how big my page sizes are and things like that to figure out how to take an actual address and divide it into its component parts. And what we're going to do now is to map the virtual page 2 into a physical page. So here we are, we're going to look at entry 2 in our page table, and we see in fact that the R bit is set, so the page is resident in memory and corresponds to physical page 4. So it's easy for us to quickly come up with a physical address for C8. So then we would go off to a physical page 4, and at offset C8 into that page, we would find the word we were looking for. Pretty straightforward. Everybody see how that worked? And it goes, it's a very straightforward process of checking the table. Yes, sir?
Where did we get the C8? Oh, because it's...
That was the page offset.
Okay,
Right. Okay. Now, a slightly different example in which we're accessing the stack and we're looking for address 604 hex. And again, what we're going to do now is quickly go look in our page table at virtual page 6. Now, that's the virtual page number is 6. It's not resident, it's on disk. So now now this is when we would take a page fault. And now we have a slightly more drawn out process where we have to go off and choose some page that we're going to actually say, well, we're going to have to take some page that's currently in physical memory and get rid of it. So our least recently used page is virtual page number E. So this is the least recently used page down there. So what we're going to do is we're going to take that page out of our mapping. We do notice, however, that its dirty bit is 1. So that corresponds to physical page 5. But its dirty bit is 1. So the first thing we have to do, since the dirty bit for that virtual page, the least recently used virtual page is 1, is we need to go off and take those actual physical page locations and put them back out on disk because they've been changed. So we're moving things from physical memory back off to disk. And once we've done that, we're now saying, okay, we're no longer going to have any information about virtual page E, page 14 here. So we clear the page table entry for that. So we've saved the information about what was on that virtual page, which was hiding in physical page 5. We've written that back out to disk, and now we no longer will be offering any storage for virtual page E. And that physical page now we're going to reuse, okay, to correspond to virtual page 6. So we go read the right information off of disk and put it into here. And when we're done, we can set up the page map for page 6 and complete virtual page 6, which now points to physical page 5. And we can complete the access in the course of completing that store now at offset 4 into this new page, into physical page 5, which now is the physical page that has the information for virtual page 6. We're going to go off and set the dirty bit because we wrote into it. Yes, sir?
The reason we replaced E was because it was mapping to someone's physical address.
Well, we wanted to basically make room in physical memory so we could bring in the contents of virtual page 6.
So what if we already had space in physical memory?
If we happened to have a free page and didn't have to kick out any existing ones, so if we had a free page, we could have just used it. In this particular example, we didn't have all the physical pages were used for storing some virtual page, so we actually chose the least recently used virtual page to throw out.
I mean, where do we check the physical memory?
I'm sorry, how do we know which is the least recently used?
How do we check if there's free space in physical memory?
So typically there would be a table that would keep track of what physical pages are allocated to what function. Right, so in some sense, we have sort of the reverse lookup table. So we could go off and like keep a list of unallocated physical pages or something like that, and use that. And if that list is empty, then we're going to have to go and figure out something to throw out to make room. If that list isn't empty, we can just borrow. If you say, great, we have a free physical page. So when you first boot up the computer, a lot of your physical pages are free. And in fact, if you go to like your activity monitor or your task manager and you look at information about the memory, it will tell you how much is free. Okay, so that would represent the number of bytes or pages that you could allocate without having to throw anybody out. And typically it's good not to start throwing things out, because if you're in the business of throwing things out and bringing them in all the time, you can hear your disk or don't have a solid state disk, but your program will run very slowly if every time it makes a memory access it has to actually move the disk. So now your memory accesses are taking milliseconds, and that would be a very, very slow system indeed. Did I see another hand up there, or no? Okay. So that shows sort of the two things that can happen, right? Either we succeed right away, or we actually have to go through the page fault process to bring in the information from disk and make it available in physical memory and adjust our page table here, adjust the MMU data so that we can now get to that virtual address at its new location. It used to be on disk, now it's in this case in physical page 5. Okay. So in general, we can think of this mapping from virtual memory to physical memory as a context, and that'll be our first step in creating a virtual machine. So the context will be part of the illusion we're creating about giving you a very large virtual address space, and at any given time only having actual locations in main memory that correspond to the virtual pages that you're using. And the ones that the virtual addresses you're not using, we don't have to we can just leave them off on disk somewhere. And so if we wanted to switch from one virtual memory to another, we really just have to switch the page map. And we've talked about that last time. So this is actually a pretty neat idea, this notion of time sharing among programs by sort of switching the information the machine has to how to translate, in this particular instance, addresses from virtual to physical. But we're going to use that now, that same basic idea, to sort of virtualize all the other resources of the machine, not only the address space, but the I/O devices and things like that. Okay, so we're going to have a separate context for each program. So that means all your programs, they all compiled to start at location 0, and away they go. And the fact that we have 5 or 6 programs running, all of which think they have a location 0, isn't a problem, because as we go from program to program to program, we'll switch the context so that virtual address 0 gets mapped to different locations in physical memory. And that happens all the time here. You probably have maybe up to 100 different programs or processes that are running in your machine at any given time, and they all happily are pretty much ignorant of each other. They're just all running as if they had their own little beta to run on, or their own little Intel chip to run on. We're going to actually put the operating system, or the kernel, we'll call it, which is a special piece of code that will help us manage our virtual machines and help us manage the changing from one process to another. So the kernel will have its own context. And that's valuable because for security reasons, we don't want user programs to go changing the operating system code. They could create all sorts of horrible security violations. So we're going to keep the kernel in its own memory system and come up with a special way in which user programs can communicate with the operating system kernel. So we'll have a rapid context switching mechanism that lets us switch between the different running programs, and we'll have a special running program, which is the operating system. Okay, so we're going to create this new abstraction called a process, which is sort of everything that we need to do to have a running program. So one of the things in the process is this context. But we also have a copy of all the registers, basically all the state of a running program, which we have the program counter, we have the register file, we have the contents of main memory. Those represent everything we need to know in order to set up the program to start running. So we can stop it at any point, save away this entire all the information that represents the actual state of the process. Save that away, and then put in the save state from some other process, and we can sort of switch process to process to process. And as I said, there's probably several hundred processes running on your machine. If anybody has an open machine and can pull up their activity monitor or something like that and just tell me how many processes that are running. I see some open in the back. I'd be interested to know. And as I say, this process switching is something that's happening all the time on every machine that we run these days. And so we're going to start our conversation about the kernel and how we communicate with the kernel and how we actually manage this collection of processes. And you can think of each process as an instance of a virtual machine. Yes, sir.
Sorry, I'm slightly confused. Each process does not have its own registers.
Yes. So R0 in your email process and R0 in your browser are different. You know, when they run, they will each have their own contents in R0. I mean, their programs are expecting the registers to, you know, have certain information in them. The programs were compiled to expect that.
But there's still only 32 registers on OpenNet.
Right. So what you're pointing out is that if we have 100 processes, it seems like we need 100 times as many registers. Okay, but we only have 32 physical registers, so how is that going to work? And in fact, one of the questions we're going to talk about in the next umpteen slides is exactly how we manage that. How do we actually make it so we can only have 32 hardware registers, but each process has its own, and you'll see it's actually a pretty straightforward. I don't even want to say trick, it's just a process, it's a method of managing the machine that will get done what we want to get done. And so if I haven't answered your question in a couple of slides, let's get back to it. Okay, so we have this big collection of hardware, and the hardware is not only the CPU. We've already talked about how we might manage access to physical memory, but there's a disk, there's all sorts of I/O devices that you might have plugged in. You have a screen and a keyboard and a mouse, and all of those are going to be managed by this special privilege process called the operating system or the kernel. And the kernel will create the illusion of a virtual machine. So you'll be able to run on the CPU, and you'll have your own, you'll be when you access a register, it will have the things that you've put into R0. There's the virtual memory system. So when you ask for a memory location, there's some combination of software in the kernel and hardware in the MMU that translates that to a particular physical address. When you want to write, put up something for the user to visualize, you don't actually write to the raw hardware buffer that represents the frame buffer for your video display. You write into this abstract rectangle of memory, this rectangle of bits in memory, that is sort of the bitmap for your particular window. And then there's operating system code that worries about how to get the bits that you're setting in your window into the actual appropriate hardware buffer. And so, in fact, the window for your email and the window for the browser, the programs just write into those bitmaps as if they had the whole window to themselves. And the fact that the email window may be on top of the browser window, the browser doesn't have to worry about that. That's the ability to figure out which windows are on top and which bits are occluded. That's all hidden in the window system, buried in the operating system. Right? If I want to access a disk, I don't actually go out and say, give me byte 17 of sector 24 of track 112. I typically think of the disk as organized as this sort of nice abstraction as files, right? And I will talk to the operating system kernel and I say, please give me byte 27 from this file. And it will worry about where physically that is on disk. So this gives us, these are designed to be easy to use. They tend to try to be, nice programming interfaces to make it simple to do the operations a program wants to do. And it's really up to the kernel to figure out how to map these abstract operations onto the physical hardware. So you can actually go off and, you can have a combination of of actual spinning hard drives and solid-state drives, and in fact the solid-state drive may be acting as a bit of a cache for the much slower the traditional magnetic drive and things like that. All of that's hidden from you. You're just saying, get me a byte off the file, and if it comes in faster and cheaper than it did 2 years ago, that's great. You haven't had to rewrite your program. You're still dealing with the same abstraction. So this notion of creating a nice abstraction barrier here is one we've seen a lot, and basically isolate the functionality, the behavior from the details of the implementation. So, disk drivers changed down here. When I put in a brand new network card for my 10 gigabit network, I don't have to rewrite all my network code. That's all hidden in the drivers in the kernel. I still access things through, the standard sockets, so forth and so on. So there's a whole collection of these virtual machines, and we're going to discuss now how the kernel actually switches between which virtual machine is running at any moment. Okay, so here's the plan. Here are these two processes running away. So I'm going to start off, I'm going to be running in process 0, and at a certain period of time, right here, this magic moment in time, so time is sort of going down the screen. In this particular case, it's virtual time. So this notion of time elapsing in process 0, it suddenly gets to the end of it's either it goes off and asks the kernel to do something, say get me another byte from the file, or perhaps a little timer goes off, a hardware timer saying your time is up, ding, and your fraction of a second that you get to use the CPU is up, and I'm going to interrupt the running of this process, and we'll talk about how interrupts work at the hardware level in just a second. But there's some way of basically suspending execution of that guy. And this guy may not know about it at all. He just says, I want to do an add. And you say, stop right there. I'm going to transfer control to the operating system. In step 2, I'm going to transfer control to the operating system. And in step 3, what I'm going to do here is to start saving away all that state information. So I'm going to take the physical registers that were being used by process 0, and I'm going to start copying them into a kernel data structure. Sorry, bang, bang, bang. So I'm going to have a special array in the kernel, which I'm going to call user. And one of the things that's in the user array is a copy of all the user's registers, R0 through R30. We don't actually need to save R31 because, of course, it always reads a 0. And there may be other things besides that, which we'll talk about here in the user data structure. Okay, is everybody happy with that? So I'm going to take the contents of the actual hardware inside the kernel here in step 3. There's actual code that's saying move R0 into location 0 of this special storage array. So I'm moving them into locations in domain memory. So I'm basically copying everything out of the hardware registers. And then what I'm going to do is to put new things. I'm going to go to a different user structure. So this might be for process 0, and if I have the same user structure for process 1, I can basically go get all that information that just like the stuff I saved away for process 0, I'm going to go retrieve it for process 1 and put it back into the hardware registers. So do you see how we can sort of make it so whenever a particular process is running, when it looks in the hardware registers, when the process says R0 in an instruction, and you actually go to the register file, it will find the thing that it put there. Right? The fact that some other process sort of ran in between when it put something into R0 and then when it read it out, because we interrupted the execution of the program, that's okay because we carefully saved away what somebody else did to R0 and restored what your contents were. So we're sort of playing this shell game, right? We're interrupting one process, and typically we say, okay, we're going to return from the interrupt and resume execution. In this particular case, what we're going to do is actually resume a different process. We're going to start a new thing running over here in step 5. And you can see process 1, which was halted at a particular instruction, starts by executing that instruction, and all the register contents are just what it expects to see, and it gets to run for a while. So we sort of have this dovetail picture here, where each process feels it's running, but between any two instructions, all of a sudden, a fraction of a second goes by between one instruction and the next as we go run some other process. And that's what's happening on all your machines now. Yes?
It seems that all of this will slow the computer down to crawl because you have continuous reads and writes and reads and writes.
Right, so let's just think a little bit about that, okay? So how many instructions does it take to take all the registers and store them into locations in main memory? So I need a store instruction. Store R0 into a particular memory location. So I might need 30 or 40 instructions to save away all this information. And it might take me 30 or 40 instructions to copy that information from another block back into the hardware. So it might be that saving stuff away and restoring might take 100 instructions or 200 instructions. Okay, if I give you, several thousandths of a second to run, I'll say 10 thousandths of a second. Okay, so your user program is many instructions? So you're executing 1 billion instructions in a second. So if I give you a tenth of you've run 100 million instructions, right? So 100 million instructions, and then I'm going to take several hundred instructions to switch to another process. So even though the overhead seems large, actually it's a pinprick. I mean, you'd hardly notice. And the advantage you get is you get this illusion of running all the processes at once. And actually, they're each running for 1/10 of a second at a time. So let's just stop for a minute. Does that overhead seem large or small? Yeah, so I mean, the idea is that, particularly with these fast machines, that the context switches are really, I mean, there's a small cost that you're paying, but it's a fraction of a percent of the total horsepower of the machine.
It would just seem that we were losing all the benefit of all the cache architecture and all that fast memory.
Right, and one thing you have to worry about is if I keep switching and I keep blowing what's in the cache, and then I have to spend many cycles reloading the cache. And so that's where we were starting to talk about, perhaps figuring out how to share, the contents of the cache physical memory, not virtual memory. So as I switched from virtual memory to virtual memory, I actually arranged the MMU and the cache to run in parallel. There was a slide at the end of last lecture that talked about that. And so, yeah, there is some loss of cache coherency, but it takes, out of the 100 million instructions that you're running, again, it might take you a % or 2 to sort of reload the caches. So it's a price that we pay. So we're paying a tax, but the tax is small compared to the benefit. Yes?
Where are we storing this user data?
I'm going to get to that. Okay, I'm going to show you some actual code here that will show you where we store it. Okay. So we basically are interrupting one process and returning to another process. And how do interrupts work? Let me just refresh your memory. So interrupts, we have this IRQ, this interrupt request. So in fact, we might hook our little timer hardware that busily has a little counter counting down in hardware, and it counts down and it counts down long enough that, say, every 1/10 of a second, it asserts the IRQ signal. And when the IRQ is asserted, what we're going to do is basically say, okay, I'm no longer going to execute user programs. I'm going to do this forced procedure call. I'm going to save away PC plus 4 in this magic XP reg. That's the one that no user program gets to use. So that's how we're going to remember where the running program was in terms of where the program counter was. And then we're going to go off and simply force a new program counter, a magic program counter somewhere in the kernel code. Now you might say, well, what about saving all the other registers? I mean, you've managed to save away what the PC was, but what about R0 and R1? Well, you're right. We're going to have to take care of that, and I'm going to show you how that works now. So interrupt handling is is a small addition to the hardware. It's just it's a mechanism for doing a forced procedure call to a magic kernel procedure. We're going to actually write code that does all the rest of the work of saving a state, and then when we're executing now some code in the kernel that actually deals with interrupt. And since there's lots of different ways in which we might be interrupted, the timer goes off, the network interface has a new packet, so forth and so on. We're going to talk a little bit about how to, what the operating system looks like. And in fact, that's really the conversation for the rest of this lecture and next lecture. And when we're all done, we'll just take all this information that we've saved away in this user data structure, put it back in the hardware registers, and then return to the user program. Where do we go when we take an interrupt? Well, the beta is very simple. When you do a reset, it starts running at location 0. And if you get an illegal operation, a so-called synchronous exception, it's going to make a forced procedure call to the instruction at location 4 in main memory. And otherwise, for external interrupts, it's going to go to location 8. So you have a whole one instruction to deal with the interrupt. And of course, those instructions are branches off to now where all the rest of the code lives. Okay, so we're going to start talking. If you looked at the bottom of our little beta time train system, you'd discover that there's these 3 branches in a row that say on a reset, go here. On a synchronous exception, an illegal instruction, go to this particular location in the kernel. These are different branches to different subroutines in the kernel. Okay. Sometimes instead of having hardwired locations, there's actually what's built in hardware is the address of a table which contains, all where to go to. So this is the so-called interrupt table. There are a lot of different hardware schemes. It sort of doesn't matter. They all arrange very quickly to get you from starting the processing of the interrupt in the hardware to where they basically just save the program counter to setting a new program counter that's somewhere in the kernel code. Okay, and the somewhere depends on what the type of exception that we have. Okay, so let's see how this is going to work. So we're going to start off by sort of dealing with this notion of time sharing and the idea of a timer interrupt. So we have a program that might want to access the time of day. And so that's something that's managed by the kernel. In other words, every time the timer goes off, it says, oh, another 1/10 of a second has passed. I'm going to go increment my data structure in kernel memory that represents the time of day. I'm going to increase it by 1/10 of a second. And then, so that's how the kernel is keeping track of what time it is. It's sort of dealing with these interrupts and saying, oh, time to add another 1/10 to the current time of day. The programs want to be able to access, the current time of day. But they don't actually try to deal with the hardware or deal with these 1/10 of a second interrupts, things like that. They basically simply will ask the kernel, what time is it? And it's the kernel that deals with all the problems of these timer interrupts and data structures associated with keeping the time of day correct and things like that. So let's see if we can follow this story along a little bit. So here's sort of the picture. So I'm going to show you code now that actually lives in the operating system, in the kernel, right? And so the first thing we have is, so here we have this big, in this case, 64-bit number that represents the time of day, in milliseconds since midnight or something like that. Then we have this user data structure, which has a little array for storing these 31 registers. So when you asked where do we store all this stuff, it's actually an array in the kernel. It's just, when you have, when you write a program, you can go off and do, allocate an array, just like you could in C or an assembly language. And here we've just written the C code that says, please give me a 31-element array. We're going to call it user, or user.regs, and that's where we're going to stick the registers. So let's see how this works. So we have this user data structure, and then this is the C code that we expect to run whenever the timer interrupt goes off. So when this function gets called, it simply increments the time of day by, well, this looks like if we're interrupting every 1/10 of a second, it looks like the time of day is in 1/10ths of a second, because we simply increment the time of day by 1. So how do we get from the hardware interrupt to running this C code? And that's what this does. So here's the clock handler. This is the code that gets run when the timer interrupt goes off. Okay, and the first thing we can see is it carefully copies all the hardware registers into this user data structure. Okay, everybody see where this? So we're taking the contents of each of the hardware registers and copying it into this array. So now we're allowed to use the registers. Now the kernel code can use the registers. No registers were used in doing this, right? I'm not changing the contents of any of the registers until I've saved all those bits away in this magic array, this kernel array. Now I can go off. I'm not going to trust the user stack, so I'm going to set up my own stack, set up the stack pointer to point to the kernel stack, and then I'm going to just do a regular subroutine call off to the clock handler, which will do whatever it would do. When that returns, I'm going to take all the registers, which probably got messed up by the C code in the handler that I called. I'm going to restore them from my magic array where I saved them away, put them back into the hardware registers, back up the XP, because the XP was actually the PC +4 of the instruction that was executed. So I want to back up what will become the program counter to point to the instruction that was interrupted, so I can now actually execute that instruction. And then I go off and I say, okay, go back to that PC and start running the user program again. Right? Interrupt, save the registers, jump to the handler. It does whatever it does. When it returns, restore the registers and return to the user. Okay, very simple little recipe. Do we have to save all these registers? Could I not save some of them? What would that mean? That would mean, of course, the kernel, yes, go ahead. We have to save the registers that the kernel is going to change, and we don't have to save the registers if the kernel doesn't change them. But because the kernel is itself a very complex program, in general, we don't know what registers the C code when it gets compiled will use. So in general, it's just simpler to write the kernel to save away all the registers. In the end, we're only saving a couple stores and loads, which in the scheme of things is a vanishingly small overhead. Okay. Alrighty. Suppose we wanted now to actually time-share the machine. If every some number of clock interrupts, we said, hey, I want to go run some other process. So let's say every 5th clock interrupt, I'm going to say, okay, it's time to go run some other process. Well, here's how that might work. I'm actually going to build myself a new array. Okay, this process table that looks like this is actually n copies of this user state. So it's a big array of these data structures, and I have something for process 0 and process 1 all the way up to process n. And there's a notion of there's a current process. So the current process is equal now to 2. I'm just reminding myself which process I'm running. And so this so-called process table here, that's what I've described here. So this is what in the slide is called proc table. Okay. So proc table is an array of all these structures, and you can see the way the scheduler works is it takes the place where the interrupt handler stored all the user registers and simply copies it into the current process. So it says, aha, I'm going to take all these registers that I saved away when I got the clock interrupt and I put down here in the kernel memory. I'm going to copy it to another place in the kernel memory, but this array here is specific to process number 2. I'm going to save it away there. I'm then going to change the current process to process 3. And then I'm going to copy all of process 3's registers back here. And then I'm going to go ahead and set up the page map, anything else I need to do to start running process 3. And then I'm going to return from the scheduler call. And when I return from the scheduler call, that means I'm going to return from the clock handler, which means I'm going to load up the registers. I'm going to load up the registers from here. So whose registers am I loading up when I return after calling scheduler? The registers for the new process, right? What I've done is I've sort of pulled a fast one on the clock handler. He says, look, I put a bunch of registers in there. I'm going to restore them. I pulled a fast one in the scheduler simply by swapping the registers that are in the locations that will be used to restore the actual hardware registers. So the scheduler is just sort of playing the shell game. You call the scheduler, it takes the listing of all the registers that the interrupt handler is going to use, copies them out, takes some new information, puts it in, and says, okay, now you can return from your interrupt, but now it's going to be returning to the black and white process instead of the color process. Questions about that? It's a pretty simple little scheme. Yes?
It also has to return, because if you just return to the same spot in the program that it left from, it would go back trying to do the old thing with the new things registers, right? So it also has to...
So one of the things that we've done, so if we look at here, where do I return to? I return to wherever the XP register is. So the XP register, R30, was where we save, that's the program counter that we saved away. So when I swapped the registers, one of the registers I swapped was the XP register. That makes sense? And so I'm actually returning to the save PC from process 3, not the save PC for process 2. So one of the advantages of putting the save PC into one of the registers is that our register swapping thing automatically switches the PCs that we're returning to. Okay. Okay. So there's a couple details. You could say to yourself, if I'm running this code here, which is busy saving the way the register because I got an interrupt, what would happen if I got another interrupt? Well, I was in the middle of the kernel, and I hadn't saved all the registers yet. Oops. Okay, so there's this notion of re-entrance. The idea of re-entering something means you're halfway through a program. Can you sort of say, wait, another interrupt and re-enter the same program, the same piece of kernel code? So in general, you don't really want to re-enter code that's busy saving state because you haven't saved all the state yet, right? So things are sort of in a confused state. So what we're going to do is come up with a process, a technique for ensuring that we never interrupt the kernel. And in fact, in Lab 6, you'll implement this. We're going to set aside the high order bit to be the supervisor bit. High order bit of the PC to be the supervisor bit. And when that high order bit of the PC is 0, that means we're in user mode and we're going to allow interrupts. But when we take an interrupt, all the PCs that we use, Xadder and ILOP and all those PCs are going to be PCs that have the high order bit set, meaning they're in kernel mode, and you will arrange your hardware to disallow interrupts in kernel mode. Right, so somebody says IRQ line goes high, the hardware says, okay, you've got an interrupt. You're going to design your control logic so that if the high order bit of the PC is on and you're in kernel mode, you're going to say, nope, I'm just going to ignore it until I return back to user mode. Right, so the kernel mode here is this sort of collection of interrupt handlers. Once you enter one of those, no more interrupts will happen, okay, until it returns back to the running program, to the user program, and now the actual hardware interrupt can happen, and you might go to some other interrupt handler. So that means when you're writing kernel code, you have to be pretty careful, because if you get like infinite loops in the kernel, often your machine just goes autistic. Interrupts are disabled. There's no way to bother the machine. Once it starts looping in the kernel, that's all it's going to do for the rest of time. So you ever notice sometimes, your machine seems to go like dead? Mouse doesn't work, keyboard doesn't work, nothing works, da, 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 da. Chances are you're probably in some kernel loop somewhere. It's not supposed to happen, but occasionally it does. And what do you have to do to get restarted? Yeah, you find the power button and you press it for 5 seconds and it powers off and you turn it back on. So that's typically indicative of a very bad bug where somehow things got caught in some sort of loop in one of these handlers, which shouldn't have happened but did, and now the machine is completely autistic. It's not going to respond to any of the goings on, on your mouse or your keyboard or on the network or all your cursing. Nothing's happening through the microphone. So, okay. So how do we communicate with the OS? How does we can say, look, it's in a different context, and we keep talking about the user program asking for the time of day. So I'm going to start that discussion here, right? How do I get to it? In other words, I really want to do a subroutine call to the kernel, but the kernel's code is not anywhere in my user's address space. So I can't simply just do a branch like I would normally do. I need some way of transferring from user mode into kernel mode in a way that the kernel says, oh, you want to know the time of day? Fine, I'll give it to you. And first of all, how can we communicate things to the kernel? If we wanted to send a message to the kernel, well, we'll figure out in a moment. We're going to use basically an illegal operation to transfer control from the user program to the illegal operation handler in the kernel. That's how the user program is going to transfer control. But how do we send messages to the kernel? Where could we do that? We can just put information in our registers, right? And if the kernel wanted to send information back to us, it could put information in our, it could basically change what it sticks into the R0 slot here. So when it returned to execution, the user mode program started re-executing. Its R0 would suddenly contain the information the kernel put there. Okay, so we're going to, these illegal operations that we're going to use is just a detecting an illegal opcode. You've started to work on this in Lab 6. So this illegal operation does exactly what the hardware interrupt does. It just goes to a different PC. So the external interrupt, the IRQ request is really, and the ILOP work very much the same. They just go to a different place in the kernel. Okay, I'm going to stop here, and I'll pick up this conversation next Tuesday. But on the next couple of slides is basically sort of walks you through the process by which an illegal operation is recognized as this magic kernel procedure call. And we'll see how the kernel and the user mode sort of interact.